Alright, now, I guess we can call this Unit 8, Unit 8, Part 16, I think. Unit 8, Part 16. Something about osmosis. Before we talk about osmosis, we have to talk about the second law of thermodynamics, which might sound kind of hard, kind of scary. It's a scientific law, and it's actually very important. So I thought I'd just mention it a little bit. We're not going to do any mathematics with it or anything, but there's this thing called entropy. Entropy is a measure of disorder, and it's given by the symbol delta S. So a Greek letter delta and then S. So that's a delta means change, so it's a change in the entropy. And for reasons I won't get into, it's hard to measure the absolute entropy, so the total entropy. So usually we talk about a change from one set of conditions to another, and we're looking at the change, just like change in temperature. Instead of looking at absolute temperature, we look at, well, we went from 10 degrees to 20 degrees, that's a 20-degree change. We do the same kind of thing here. I won't talk about the units for entropy, but it's a measure of disorder, and the reason I mentioned it's delta S, you can think of S as a sloppiness factor. I spell sloppy. This factor, so the amount of disorder or randomness. And the thing about the second law of thermodynamics is the entropy of the universe is always increasing. The universe is always getting more disordered, so entropy is always increasing. This explains why your coffee cup cools down when left by itself. So here we have your coffee cup, and it's hot, right? And heat is leaving the coffee cup, so it's getting colder, and it's going out into the universe. And it's not going to heat up the universe a lot, right? But theoretically, as the heat leaves this coffee cup and goes out into the universe becomes more disordered, more random. Particles are moving around faster as the heat leaves. So the coffee cup cools down, and the entropy of the universe increases. In a less scientific way, but still entropy nonetheless. You can think about your car. Your purse always gets messier, more random, more disordered, unless you put some effort, some work into straightening it up. Okay. Similarly, a drop of food coloring always diffuses into the solvent and becomes less concentrated. It never gets more concentrated. So, for example, this idea of diffusion. Diffusion is a movement of particles from high concentration to low. This happens automatically, or what we call spontaneously. Which is, they say, happens or occurs automatically. Occurs spontaneously, all by itself without any help from anyone else, and that's because it's following the second law of thermodynamics. It's going from a high concentration, which is ordered, to a low concentration, which is, we could say, less ordered, or if you wish, more random, or sloppy. For reasons I won't get into, it has to do with statistics and probabilities and whatnot. I won't get into why a high concentration is more ordered and a low concentration is less ordered or more random, but turns out that's the way it is. And from our experience, if you take a drop of green food coloring in this case, and you put it in here, it's going to go from this high concentrated drop, looks like they put in 2 drops, it's going to become more and more diffuse, more and more randomly or evenly distributed, and eventually the whole glass would have this green tinge to it. Okay, so again, it's going from a high concentration right? As this drop diffuses out, we go from a high concentration, right, to a low concentration. All right, so that's diffusion, movement of particles from high concentration to low. Osmosis is a little bit different. Osmosis is not the movement, if you notice here, let's back up. This is a movement of solute, the stuff that's dissolved. So this is solute particles. Osmosis is a movement of water. Well, water is the solvent. Okay, so it's a movement of water through a semi-permeable membrane. We'll talk about what that is in a moment. The level of solution with the higher concentration rises. So here we have pure water. Here we have water with some sugar, sucrose dissolved in it. So we have water and a solution. Right, here's our solution. This is just pure water. No solute particles, little solute particles here, right? So no solute particles here in the pure water side. And they have equal level here, right? The levels of the side with the higher concentration rises. So you see this right, goes up. This level went up. Okay. Well, why did it go up? Well, because water passed through the semi-permeable membrane from the left to the right. So pure water, they show it down here. Pure water is going through the semi-permeable membrane. The semi-permeable membrane has itty bitty tiny little holes in it. And if you think about it, water is pretty small. It's only 18 grams per mole. Just made up of 3 little atoms. Sugar, on the other hand, these solute particles, I believe it's like 330 or 360? I don't know. It's around 330 grams per mole. Much larger. Actually, the formula is, what is it, C12H22O12. So you can do the math and figure out what the molar mass is. But they're much larger than water. Consequently, they can't fit through these tiny little holes. So that's why they call it semi-permeable. Semi meaning kind of, halfway. Well, half of the stuff can get through. The water can get through, but the larger solute particles cannot. Right? So just as just as diffusion was a movement, what was diffusion? Movement of particles from high concentration to low. Right? What this essentially does is let's go back here. We say diffusion occurs in the direction to eliminate concentration, that's CONC, concentration differences. Right? And I don't have a picture here of the glass where it's a uniform green, but if we waited long enough, this green food coloring would be evenly distributed and there would be no concentration difference. It would be evenly distributed. Okay, so that's diffusion. Similar kind of thing happens here with osmosis, but it's not the little green solute particles moving, it's the water moving. And the water moves in the direction so the two solutions become, concentrations become equal. So which way must the water flow in order to equalize the two concentrations? In other words, which side must get diluted? Well, we have pure water on one side, a solution on the other. The water is going to move from left to right. This volume increases. This side becomes more dilute, so water is going to keep going from left to right in an effort to dilute this so the two concentrations are the same. Semi-permeable membrane. What's a semi-permeable membrane? Well, be sure to speak slowly so it has a chance to sink in. It looks like we're only dealing with semi-permeable membranes here. No, not membranes. Not membranes, but I misspelled that here too. It's membrane. Got my M and I N's mixed up. Membranes. So cells, biological cells, right? They have a cell wall. I don't know, maybe this is a some blood vessel or something, and there's little pores, little holes in this cell wall of this blood vessel that allows small particles like sugar or sodium chloride to pass through, but the large red blood cells can't, right? So you've seen, maybe you've gone to the zoo and you've seen this is a semi-permeable membrane. Got a tall, thin door here, or allows Joffrey the giraffe here to get out, but I can't draw an elephant, so I'm not going to attempt it. But big, fat, wide elephant can't get in, right? So here we have a semi-permeable membrane designed to fit this giraffe. Similarly, we have pores in the side, in the cell walls or cell membranes of organisms, so that certain size can get through, but the larger ones can't. All right. So osmosis, right, is a movement of water, and it moves through a semi-permeable membrane in an effort to make the two solutions equal. So we have a 4% starch, we have a 10% starch. So let's say this is 4%. It doesn't matter by mass by volume or whatever. If it's 4% starch, that means it's what? That means it's 96% water. Right? If it's 10% starch, so it's darker color, let's say it's green starch. If it's 10% starch, it means it's 90% water, right? 90 plus 10 is 100. So which way does water go? Well, it's going to go from the higher concentration of water, which is 96, to the 90. So this is a higher, it's a lower solute concentration, but a higher water concentration, and it's the water that's moving. It's the lower solute concentration, higher solute concentration. So water goes from the high water concentration to the low water concentration. If you want to think of it that way. So in that way, because it's the water that's moving, it's really just like diffusion. Diffusion is a movement of particles from high concentration to low. But with osmosis, two key critical things here. One is a movement of water only, and it's a movement through a semi-permeable membrane, right? The second law of thermodynamics would tell us that, hey, you know, we have a concentration difference here. We should get a movement across this membrane to equalize these two concentrations. But the starch is really a very large molecule. It can be in the order of hundreds of thousands of grams per mole. So it can't get through this little membrane, but the water can. So the water goes from the left side to the right. Over time, this side would the volume would increase. The volume increases. That means this concentration, this 10%, would drop. Right? Similarly, this volume would decrease. Why is it decreasing? Well, because water is leaving this left side, going to the right side. So the volume decreases. Eventually, they would reach an equilibrium where they're both, what would be 7%. Okay, one side goes up, the other side goes down, and they're both 7%. Right? At that point, water is still going back and forth, but every time a water molecule goes from left to right, another one goes from right to left, so they're in equilibrium. Okay, so eventually the water flow between the two becomes equal, and the concentrations are equal. Osmotic pressure. So osmosis is a process. Osmotic pressure, this is a colligative property. And osmotic pressure is simply the pressure required to prevent osmosis from occurring. So it's equal, it says here, equal to the pressure that would prevent the flow of water into the more concentrated solution, or in other words, into the to dilute the more concentrated solution. Okay, it's a colligative property, so the greater number of particles dissolve, the greater the osmotic pressure. me just draw a little picture here. Actually, yeah, let's say we have that first example I had. I can't remember what the concentration was. We've got a semi-permeable membrane here, and I don't think there was a concentration, but we had pure water on one side and we had sugar on the other. So let's say this is 20% sugar, 20% sucrose, and the two levels are the same. Okay, and we allow some time to pass. So some time passes, and what happens? Ignore the 25 there. There's our semi-permeable membrane. All right, so water is going to go in the direction to make the two solutions equal. So clearly, we can't dilute pure water, but we can dilute the 20% sucrose. So water goes from left to right. So this side gets higher, this side gets lower. And even if this side doubled, so now it's maybe only, it's the volume doubled, so now maybe it's only 10%, we still have pure water on the left. Okay. So why doesn't all the water go from the left to the right? Well, because of the difference in these two levels, water always wants to seek its own level, even through a semi-permeable membrane. Right? But there's a greater mass of water pushing down on this side and essentially preventing the flow of water. Water still wants to move through these membranes, right? But we have the osmotic pressure owing to the larger, what we call hydrostatic head, or the larger height of the water here. And you can measure the force of this. You know maybe the dimensions of the vessel, so you can measure what volume this is by measuring the height and you know the mass of the. Whoa, what's going on there? That's weird. You know the mass of the water, so you could calculate the force of water pushing against it by the difference in the height, and whatever height is required, whatever force of this water is required to prevent osmosis from occurring, that's the osmotic pressure. So we just wait some time until this reaches equilibrium, and the water, how do we know it's equilibrium? Because the level of the water isn't changing anymore. Right? And what does that mean? It means as every time water goes from one side, left to right, it also goes from right to left, so the levels don't change anymore. It's at equilibrium. We measure the height. We could calculate how much water that is and how much force it's exerting. That force is the osmotic pressure. It's equal to the pressure that would prevent the flow of osmosis from occurring. Okay. Learning check. Solution blank has greater osmotic. So we got two solutions. A is 10% starch and B is 5% starch. Which has a greater osmotic pressure? Well, the one with the greater concentration. Right? So B. Water initially flows from what? It's going to flow from the lower solute concentration to the higher. It's going to try to dilute this higher concentration. So it's going to flow into A. It flows from B into A. Right? In an effort to dilute this higher concentration. The level of solution what will be lower? Solution B will be lower because it's flowing from B. Water is exiting the B side. So B will be lower. A will be higher. Oops. Solution B, I got this mixed up. Solution A is a 10%. I hate the way they do that. A is a 10%. So it's, sorry about that. There we go. That's better. Solution A has a greater osmotic pressure, has a greater concentration from B into A. B is lower, A is higher. Okay. there's a few more terms I want you to know. It has to do with blood cells. Okay. Iso means the same. We talked about isotopes, right? These are atoms of the same element, so iso means the same. An isotonic solution, known as a physiological solution, has 5% glucose and 0.9% sodium chloride. Okay. This means that water enters and leaves this red blood cell at equal rates, so it's in equilibrium. And we have a happy cell here. So we've got a smiley happy cell here. Okay. So isotonic means the same osmotic pressure inside and out of the cell. So it's the same inside and out, so water is already in equilibrium. We have the equal rate going into and out of the cell. Hypotonic. What happens in a hypotonic? Hypo means low, like a hypodermic needle goes under the skin, under the dermis. A hypoventilation is a low respiration rate. So hypo means lower. So we have lower on the outside, higher than on the inside. The solution is lower. Right? The red blood cell is a red blood cell, but we can put a red blood cell in different types of solutions. If we put it in a hypotonic solution, lower concentration, what does that mean? Lower than 5% or 0.9%. So less than 5% glucose or less than 0.9% sodium chloride. What happens? According to the second law of thermodynamics, water will enter the cell at a higher rate than it leaves. You know, so you've got a longer arrow here. So water enters the cell, and the cell gets bigger and bigger. The cell volume increases. And it can increase so much that tears start occurring in the cell wall, what we call hemolysis, right? So the cell wall breaks and the red blood cell dies and it squirts its guts out into the bloodstream or into the beaker or whatever. So hemolysis, they don't say this, but the cell dies, right? Causes water to flow into red blood cells, causes hemolysis, swell, and burst. Well, they don't have the opposite. Oh, there it is. How did I? Hypotonic. There we go. Hypertonic. Hyper, hyperactive, more active. Hyper means higher concentration. So higher concentration in the solution than in the red blood cell. It's a funky looking red blood cell. Looks like a macrophage or something. But what's going on here is the concentration on the outside is greater than this 5% glucose, or greater than the 0.9% sodium chloride. So what happens? The red blood cell, poor little red blood cell, is trying to dilute this higher concentration, so water leaves the red blood cell. Right? Water flows out of the red blood cell, and it causes the cell to shrink. This is what we call crenation. This also leads to cell death. Okay, so water leaves the cell, it gets dehydrated, shrivels up, dies. Why do fingers get wrinkly? I thought this was a hyperlink. Maybe not. Anyway, back when I was first told this, I was told that, well, fingers get wrinkly because the skin on your fingertips is thicker and it has to do with osmosis, and it turns out that's not the fact. Actually, it's a involuntary response, and they suspect it might have something to do with being able to grab things when they're wet, and it's actually a nervous response. So when you have people with nerve damage on their fingers, they don't get this. Well, then clearly it's not something to do with osmosis and just the second law of thermodynamics and semi-permeable membranes and the flow of water. It's some kind of nervous response, so something with the autonomic nervous system. So this article here talks about that. But pickling certainly does. So here we have a regular sized cucumber. So here we have a cucumber. And then inside we have a pickle. So what happens is if you put a cucumber in a briny solution, what does that mean? A high salt concentration? In other words, this is a hypertonic solution. What happens? Well, the water leaves the cucumber and goes into the briny solution. So what happens is the water leaves, the cells of the cucumber shrink or crenate, and the cucumber gets smaller until we call it a pickle. So, example of crenation. All right. Dialysis. How many more slides we have here? 34, 35. I am going to skip dialysis. You're welcome to read this through if you like, but you won't be seeing any of this on the test. The only reason we mentioned dialysis here is because if you remember, colloid particles were too big to pass through these semi-permeable membranes, so it'd be like protein or starch, but solution particles can. Right? So the protein stays in these large particles stay in the dialysis bag, and the little solute particles can escape, so they pass through the semi-permeable membrane. You can get dialysis tubing or dialysis membranes with all sorts of different size pores, different size holes to select different size particles, and essentially this is what's used to purify blood through hemodialysis. Right? So if you know anyone who has kidney disease or something like that, and they have to go in for a dialysis treatment, essentially what they're doing is it's kind of like osmosis, but instead of the water that's moving, it's the particles that are moving through the semi-permeable membrane. There's also something called reverse osmosis that's used to purify water. And unfortunately, we don't have time to talk about that, but if you understand how dialysis works, then if you were to read something online about reverse osmosis and water purification, it should make sense to you. So I'm not going to test you on dialysis or hemodialysis or reverse osmosis, but it's here if you care to look at it. All right, so that will do for this lecture.